Blah, blah, blah. Oh, unfortunately, I can't go over the, I cannot go over the solution to the test with you guys because I don't have the, I have the wrong computer here. I don't have the solution in it. So sorry about that. We can go over the solution to the test later when we have our review for the final day, all right? So if you're really itching for me to talk through the solution, I can make a video before then. If you want, just email me and ask me to do it. Yeah.
When will these be put into the grades on
I put them into Canvas.
Yeah.
I did, but I would remind you guys that because I drop, I mean, you can look at Canvas and you can see what your current percentage grade is, but it doesn't mean that much because I will replace your first and second test grades with your final exam score if it's helpful. So like whatever percentage you have, that's the worst case scenario, right? Actually, that's not even meaningful because really, I really think you should always think of course grade in terms of points lost, right? So like what points have you lost? So your missions are worth 100 points apiece, right? So hypothetically, if you make a 50% on all three missions, you've lost 150 points. That means that you can't make an A, right? On the other hand, if you have a 60 on mission 1, an 80 on mission 2, and a 90 on mission 3, you've lost 10 points on the last one, 20 points on the second one, and what would I say, 60? Yeah. 40, so 40 plus 20 plus 10, around 70 points. You lost 70 points if you made those scores. So you can still make an A on the final in principle, although I do also need to calculate quizzes. Like your quiz grade is what it is. I think quizzes are 100 points total in this course, right? So there's more than 10, so I have some bonus points in there basically, if I remember right. Listen, I can get back into flesh out the details here, but that's really not worth our time at the moment. My larger point to you is you can't just look at Canvas and assume that that's like the grade that you have or the one you're going to make. You have to think through the points in the syllabus, all right? If you want me to talk to you about it, I can. Yeah.
When's mission 2 going to be graded?
Oh, so the grader said that she had a test or something, so she's gotten behind, but she did. I gave her the quiz that you just got back and mission 2 at the same time, so she's been really fast. Like I think I gave you guys like mission 1 to her, and she had it back the next class, like Thursday to Tuesday. So she'll be fast when she gets to it. She's just gotten behind in the semester. For whatever reason, her semester, she's gotten like a couple tests, so that's the delay. It is not forgotten. It's not lost. So it hopefully next class, I would hope. That is a good question, though. It should be soon. Any other questions? So I will try to once we get, like I said, once we get mission 3 graded and we have all those grades set, then I'll try to, maybe even before then, maybe because mission 3 might not be graded until like the day before your final or something. I'll probably once mission 2 is graded and we've got like one more quiz, we have a pretty good sense of like more or less where your score is going to be. So then I can do something like, assuming you make the same grade on your mission 3 that you made on mission 1 and mission 2, I can give you some kind of estimate for what kind of score you need to make on the final, in order to get whatever grade, A, B, C, and so forth. Now, again, if you have missed a lot of homework, you may have done enough damage to your grade that you can't make an A, but if you're a person who hasn't done all the homework, you probably were not aiming for an A anyway, if I had to guess. I could be wrong, but I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you just bless our work today. Help us to understand exponentials and logarithms and how they work, Lord. In your name I pray, Lord Jesus. Amen. I think I gave you guys the top hat. Yeah, I tended to cheat around. So last time I showed you what an inverse function is, right? Now I need to define exponential functions. What's an exponential function? A function using exponents? I mean, that's kind of true. So it's something like this. F of x equals a to the x is an exponential function with base a. All right, so we're going to assume that a is positive here, okay? A is going to be greater than 0 in everything we do today. Let it be understood. Okay, so this is an exponential function. Now, we've worked with this kind of formula before, right? What's the difference? Let me just, before I go any further, let's just talk about something. If I had g of x equal to, let's say, x squared, it's the same kind of formula, isn't it? Right? But this is not an exponential function. This is called a power function. I mean, it's also a polynomial, but this is specifically a power function, power 2, right? In contrast, if we looked at, example 1, f of x equals to 2 to the x, this is an exponential function with base 2, right? It's the same kind of formula, but the difference is the variables in the exponent, whereas with a power function, the variables in the base. See the difference? Now we can graph this, right? How do you graph a function? Well, the first thing you can do to be kind of, lazy is just make a table of values. I guess it's not being lazy, it's just being unimaginative. So if I put x here and I put y equals 2 to the x, we can make a graph of this thing. Let's do it. All right, so let's pick some nice values. How about like -2, -1, 0, 1, 2. Those are 5 good values to kind of understand what this is. So what is 2 to the -2 equal to? I'll write that over here. What's that? 1? Wait, what? No, 2 to the 2 to the -2 is 4? But you're right, 2 to the 2 is 4. I agree with that. But this is what? This is 1 over 2 to the 2, right? So 1/4, right?
Yes.
2 to the -1 is 1 over 2, which is 1 over 2, right? So let's see here. So what you have is 1 over 4, 1 over 2. What's 2 to the 0? 2 to the 0 power is not 0. It is in fact equal to 1. So any positive number to the 0 power is defined to be 1. That's 1. 2 to the 1, what's 2 to the 1? Yeah, 2 to the 1 is just 2 again. And as you said, 4. And so we can plot this, right? So it's got a y-intercept of 1. It goes to 2 when you're at 1, right? And by the time you get over here to 2, you're all the way up to 4, right? When you get over here, when your x is -1, you're at where? You're at half. When you get x -2, you're at a quarter. Let me connect the dots with a different color. So this is what we got. So something like this. So here you go. This is the graph, roughly speaking, y equals 2 to the x. Question, what is 2 to the 1.5? How can you figure that out? Well, my suggestion would be you get a calculator, like so, right? And you put in 2. If you look in your calculator, you should find you should find like a power thing somewhere in there. And then I just plug in 1.5 there, and it tells me this is approximately equal to 2.83. Now that's not the exact value of 2 to the 1.5, is it? Right? It's not. So let's talk about exact values for a second here. So if I have 2 to the m over n, how can I understand that? What does this mean? 2 to a fractional power, how does it work? You can look at it this way. It's 2 to the m, right? And then you take the nth root of it. Or you could write it as the nth root of 2 raised to the m power. Them's your choices. So as I think about, if I want to find the exact value of 2 to the 1.5, you know, in terms of roots and such, what is 2 to the 1.5? It's actually 2 to the what? 2 to the, what we got here? That's 3 halves, right? So this is actually, I could either write it as the square root of 2 to the third, right? Or I could write it as the square root of 2 cubed, right? So in other words, 2 to the 1.5, if you want to write it in terms of an exact expression, it's either the square root of 8, or you could write it as the square root of 2 cubed, right? Are there any other ways we could express this? If you remember like high school or whatever, you probably would be, you know, if they put this as an answer, they'd be like, no, you're wrong, because they wanted you to do what? Like just keep as few square roots as you can, right? So if you look at square root of 2 times square root of 2 times square root of 2, what is that? Yeah, it's square root of 8, but now you got me writing 8. So these two 2's, 2 square roots, right? That just gives you 2, right? The other way you could write this would be 2 root 2.
Oh.
So, you know, if you're checking your answer in the book, that's the kind of thing you might find as an answer if it's looking for an exact value. Question though, do exact values help us graph? I don't think they do, for the most part, right? So putting the thing in the calculator, it gives us an exact thing, right? 2.83. See, so when we're at 1.5, right here, right? See here, 1.5. If I did it right, x equals 1.5. Where does it intersect the graph? Right here, right? What's that point? That point would specifically be 1.5, comma, 2.83-ish. The thing that's interesting is we can calculate 2 to any power, all right? Even if the power is not a rational number, we can still, it still makes sense to talk about 2 to that thing. So this is some sophisticated mathematics going on there to really do it justice, you know? Like, what do you mean when you talk about 2 to a non-rational power? Well, the thing is you can take any number which is not a rational number, you can find a rational number that's really close to it, and so you can calculate that. All right, let me shut up about this. So this is the graph of y equals 2 to the x. What would the graph of y equals 3 to the x look like? Actually, let me put both of them up. So here's 2 to the x, roughly speaking. Let me put some reference points here. This is 1. This point over here is what? Well, if I did it right, it should be here, I guess. There's 2, right? You get over to here, supposedly up at 4 if I could do it right, all right? And then over here, where are we? This would be 0.5, right? Okay. Now if I graph y equals 3 to the x, what does it look like? It also has some same things, right? Like 3 to the 0 is what? It's 1. So it also goes through it also has a y-intercept of 1. All right? Where does it, when you get to 1, where is it? 3 to the 1 is what? 3. So it's up here. It's like here, right? When you put 3 to the minus 1, what do you got? 1 over 3, right? That's 0.33. Is that above or below the red graph? See, it would be below, right? 1/3 is lower than 1/2, right? If you get to minus 2, it's at 1/9, whereas the other one is at 1/4, you know, and so the story goes. So the interesting thing here is that the 3 to the x graph is below the 2 to the x graph if we're to the left of the y-axis, but then when you're to the right of the y-axis, it's above. Okay, so there's your y equals 3 to the x. And you see what's going to happen, right? If we go to y equals to 4 to the x, it's going to be steeper even. Y equals 10 to the x, it's even steeper than that one, right? What would happen if we had like, you know, well, okay, that's enough for this one. I don't want to get too busy on this graph. There's one other thing I want to add. There's a number between 2 and 3, right? Let me see if I can. So to properly explain this, you need calculus. So it's just I can't disguise it. It's an issue of calculus, all right? But basically, this is the thing. If you look at the tangent line, so the tangent line to the red curve, right? This has slope about 0.69. That's the slope to the y equals 2 to the x graph. If you look at the slope of the y equals 3 to the x graph as it crosses the y-axis, it's something like this, all right? And this purple line has slope, oh, I don't know. Give me a second, I got to cheat. I don't remember that one off the top of my head. It's got a slope of about 1.1 if you work it out. And you could work it out, just plug in points and like you could find nearby points and calculate the slope of a little line that kind of is close to the graph if you wanted to. This is something you could do. I don't think you guys should do it. It's not worth your time, you know. You have other more important things to attend to, right? Ring by spring, these sorts of things this year. So, wait a minute. I don't know. What are you guys seniors or juniors? Oh, you can. What am I talking about? This is Liberty. You can get married mid-college, right? It happens. That's right. That's right. That's right. I'm not familiar with this, but okay. Whenever I teach, oh, you're already married? Okay. Well, there you go. Now you just need to have some. Oh, you didn't ask me to be in your wedding? That disappoints you?
No, I did.
I didn't respond?
Yeah.
Oh.
It should have showed up in your inbox.
I'm sorry. So guys, if you look at this, right, if 3 to the x has a tangent line, like a line which just kisses the 3 to the x function at the y-intercept, and it has a slope of 1.1, right? And y equals 2 to the x has a tangent line at the origin, in other words, that line which just touches the graph and then goes off, right? You guys know what a tangent line is? How many of you had geometry in high school? You guys know what a tangent line is? It's this one, right? Aw, man. There, use your curses. I tried. Line first, circle second. There we go. Okay, so tangent line. The tangent line is the line which just touches the circle at one point, right?
Wait, when did we bring in circles?
I'm talking about tangent lines. So the same idea.
There's a tangent line to this, right?
That's what I'm saying. These dotted lines are tangent lines to the graph. They just touch the graph at that one point and they kind of just go off. All right, so this is slope 1.1. This is slope 0.7. Think about it. There has to be some other base between 2 and 3, right? Where the tangent line has slope 1. So in between the 2 to the x and the 3 to the x graph, there is a third one, like these. This guy here, all right? And that one has tangent of slope 1 at y-intercept.
To the y equals x or 3.
What's that?
Wouldn't it be much closer? Oh, that was really close. Wouldn't it be much closer to the y equals 3 to the x power?
Yeah, it is closer to that.
It wouldn't be like right in the middle.
You're not wrong. You're not wrong. And this, so this by definition is f of x equals to e to the x is the exponential function. This number e is the number which makes the tangent line have slope 1. And you're right, it is closer to 3. In fact, e is approximately equal to 2.71 something or other. All right? You want to find out what it is?
Where is that number from?
What's that?
Where is that number come from?
It comes from the slope being 1.
Can you walk me through that process one more time?
Oh, well, we have to define the limit as h goes to 0 for the tangent line. So if you want me to walk you through that, you'll have to take another course with me.
I mean, are you going to ask us to find e or not?
No.
So then never mind, I don't need to know.
Well, yes, I will ask you to find e. Get your calculator. Find the e button. Put 1 in it.
Oh, nice.
What do you get? 2.718281828. There you go. There's the rest of the digits. And it goes on and on forever and ever. It never repeats. This is not a rational number. It's an irrational number. It has a non-repeating decimal. I can give you a formula.
No, it's fine. If you don't need to find it, then I don't know.
You started me down this path. You can't stop me. So the formula is 1 plus 1 plus 1/2 plus 1/6 plus 1/24 plus 1 over 120 and plus so forth and so on. If you keep multiplying the denominator by the next number and adding it, that actually accumulates to e.
Oh, the bounce was a good strategy.
Yeah. So this e, what do you think e stands for? It's like the shrieking of the students on the next test. E. No?
Exponent.
Sorry. Oh, exponent? That's a good guess, but the answer is less exciting. It is Euler. As in Leonard Euler, the...
Is that pronounced Euler?
Euler, yeah. It's French. So...
French.
I know, well, once upon a time, the French did some, like, pretty useful stuff. So, baguette. Why are they called French fries anyway, by the way? What's that? They came from Belgium? I guess. The French fries seem very, very detached from French food as I know it, It's a strange thing. Of course, what do I know of French food? Really nothing. But, okay, so this is the exponential function. This is an important special case, all right? And I can't give you a complete definition of what e is because it's calculus, all right? I did the best I can in here, it's that. Okay, so when I talk about the exponential function, I'm talking about e to the x. If I'm talking about an exponential function, I'm talking about some other base, all right? What other bases are there? Well, you can have base 2, base 3, base whatever, all right? Let's see here. The other thing I should talk about is what happens if we have y equals like 0.5 to the x. How's that go? So can you think of another way to write this? Well, this is really 1/2 to the x, right? So that's actually 2 to the... Okay. 2 to the minus 1 to the x, also known as 2 to the minus x. So we talked about transformations of graphs. What happens if you take y equals f of x and you replace it with y equals f of minus x? What's that do to the graph? It just does what? It flips it over the y-axis, right? So this one has the graph that looks like this. So in other words, this is also the same as y equals 1/2 to the x. And its y-intercept is 1. It's going through a half over here. 1 comma 1/2, right? If you get to -1, it's up at 2, and so forth and so on, all right? So, oh, did you move over? So let me summarize what's going on here. There's really 3 cases. Three cases, right? You've got ones that look like these. You've got ones that look like that, right? So what's the difference? This, generically speaking, is y equals a to the x for a greater than 1, right? The red one is y equals a to the x for 0 less than a less than 1, right? So if the base is less than 1, it flips the graph over, all right? They look different. And then what else? What's the other choice that we could make if a is positive? This is a very silly graph. What is it? I've got less than 1, I've got greater than 1. You could also have equals 1, right? And equals 1 would look like what? Just this, right? Here's y equals 1 to the x, also known as y equals 1. So it's generally agreed upon that that is not an exponential function, right? Would you agree? Is that an exponential function? I would say no, not really. That's a constant function, right? So what is my definition of exponential function that I gave you at the start of class need to? I need to add some strings to that, don't I? It's not quite true, is it? Like, you mean you lied to me? Well, it was a sin of omission, not commission here. So what's the fine print I'm missing here? I think what I should tell you, going back here, is we have 0 is less than a is less than 1, or a is greater than 1. In those cases, it's a genuine exponential function. Okay? Question. What's its range? What's its domain? What's that? It is not a rhetorical question. I'd like an answer. What's the domain of a to the x? Right? Yeah, everything, right? The whole kit and caboodle. What's the range of a to the x? Again, we're assuming here a is not equal to 1 and a is positive, okay? What's that? 0 to infinity. And 0 is not included, is it? It is not. What's that? That's a not included, one of these deals. All right. So just positive outputs. Now my next question to you is, does this function have an inverse function? What do we need for this function to have an inverse function? It needs to be what? 1 to 1. Is the exponential a 1 to 1 function? Yeah, I think it is, right? If you look at the horizontal line here, cutting through these graphs, it doesn't cut through more than 1 point, right? Clearly, in fact, this is a property, theorem, if you will. Property of the 1 to 1 function. If we have a to the x equal to a to the y, that implies, in fact, x is equal to y. So this is the 1 to 1 property of the exponential function. This is true. All right, this is a true thing. So this is one way you can solve equations that involve exponentials, is you can use the 1 to 1 property. All right. I can show you an example of that before we go on and talk about inverse functions if you'd like. But I think our time is better spent if I focus on the inverse function discussion. So I'm going to resist the temptation to show you examples about the one-to-one property right now. We'll do it in a future day, okay? Okay, so it has the one-to-one property, which means that it has an inverse. So here's the definition. Let's see here. If f of x is equal to a to the x for 0 less than a less than 1 or a greater than 1, then f inverse of x is denoted log base a of x for x greater than 0. So the inverse function is called the log base a. Log base a. What are the equations that log base a satisfy? So like we have these things. So first of all, a, if I take a to the x, right, and I feed it to log base a, what do I get? I get back x. All right? One of the things I get. The other thing I get is that a to the log base a, let's say of y, is equal to y. So this is for x in the real numbers, so for any x, okay? For any real x. The y is only true for positive y, okay? That's for y greater than 0. So this is one of our guiding principles going forward. If you have a logarithm, its input has to be positive. Because the input to the logarithm is the output of the exponential function. Since the output of the exponential function is positive, the input of the logarithm must be positive. It's inescapable. If you find yourself writing a log of a negative number, you need to throw that number out. It's not part of the solution you're looking for. All right? Any questions?
So we just always disregard the negative logarithmic number?
Yeah, if you work out, we'll work out equations here in about a week, and some of those equations will bring in extraneous solutions. So like one of the way we rule them out is if they force us to take a log of a negative number in the original equation we're solving, something like that. Or just if you want to find the domain. So like example, what am I on? Example 4. If my function was like this, like f of x is equal to 3 plus 2 times the log base 2 of x minus 7, and if I wanted to find the domain of this, what would the domain of this function be? So for this to be reasonable, I need the input to the formula for the log. I need that to be positive, right? So I have to solve x minus 7 greater than 0, which gives me x is greater than 7. So the domain of the function that I have right there is equal to 7 to infinity. Not included, of course. What does the graph of the logarithm look like? Let's talk about that. All right, so let me put up here's my best attempt to graph 2 to the x again, all right? Is y equals 2 to the x. Let us plot the inverse function to y equals 2 to the x, okay? So to do that, how do we do that? Well, what we should do is we should track a few points. some nice points to track are this. You got your 0, 1. Up here you got your 1, 2. Up here further you've got your 2, 4, as we talked about, yeah? Sorry, they're getting kind of tiny, my bad, but oh well. Over here you got your minus 1, 0.5, right? I can make do with that, you know, I'll just use this much. So what does the graph of the inverse function look like, right? So y equals to log base 2 of x. This is the inverse function to 2 to the x. How do you find the graph? What do? We flipped x and y, right? Just flip x and y. So here I go, instead of having minus 1.5, I have 0.5 and minus 1. So that's like here-ish. And instead of having 0, 1, I have 1, 0. Instead of having 1, 2, I have 2, 1. Instead of having 2, 4, I have 4, 2. Let's see here. So it looks something like this. All right. And let me comment on what these points mean. So that's 0.5, minus 1. Here you got 1, 0. Here we had 2, 1. This point here was 4, 2. Let me explain further what those mean specifically for the log base 2. Well, let me just do half of it. You guys fill it in. Log base 2 of 1 is equal to what? Log base 2 of 2 is equal to what? Log base 2 of 4 is equal to what? So guys, can you tell me?
Log base 2, 1 would be 0.
Mm-hmm. 0.
And then log base 2, 2 would be 1.
Mm-hmm.
Log base 2, 4 would be 2.
Right. So another one here, log base 2 of 0.5, right? Let me write that a different way. That's log base 2 of 2 to the minus 1 power. Right? So it is equal to minus 1. Of course, that's also apparent on the graph that I just wrote. But so remember, guys, I told you last class that when we look at a function and we look at its inverse function, their graphs are related but not the same. There's a horizontal asymptote for the exponential function, right? But there's a vertical asymptote for the log. Do you see that? So the horizontal asymptote for the exponential function in some sense becomes the vertical asymptote for the logarithm. Okay, let's see here, example 5. Suppose you have x equals to, I don't know, 2.6 times 10 to the 18th power. You guys ever seen this before? This is what? This is, maybe you've seen this in your science class, right? This is scientific notation, right? You multiply a number at the start times the power of 10. Yeah, this would be what? Explicitly, this is 2 comma 6. How many?
18 to a lot of zeros.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
It'd be 17 zeros, right? Because when it moves over from the 6, that's 1. When you move 17 more.
Oh, yeah. Oh, man. Son of a gun. I should have started my comma from the other side. You're, you believe in science? Good for you. I believe in freedom. Let's see here. So, sorry, that was unnecessary. Sorry, but look. So that's a huge number, right? But here's the really cool thing about logarithms. If you calculate log base 10 of this number, all right. And so, oh, well, rats. So I need a property that I haven't told you about yet, but I should soon tell you properties of the logarithm. I've put the cart before the horse. My apologies. Properties of the logarithm. If we have log base a of, let's say, x times y, that's log base a of x plus log base a of y. If we have log base a of x over y, it's log base a of x minus log base a of y. And furthermore, if we have log base a of stuff all to the power p, well then it's equal to p times the log base a of stuff. It's important that all of the stuff must be raised to the p power, right, in order to use this, I call it the power property of the logarithm. Now, my exposition today of the mathematics is especially lopsided because I really should tell you the properties of the exponential function before I do this, all right, so my bad. I blame you guys. It's the question one of you asked, surely one of you in the back row, it's all your fault. You like it's here. So log base 10. So we have actually log base 10 of 2.6 plus log base 10 of 10 to the 18. All right. Now, log base 10 is also known as the common log. Common log, and it's unfortunate. So here's the thing, in science books, log without a thing, in American textbooks, log without a thing is typically just denoted like this. All right? But there's something else, which is called the natural log, ln, natural log, which is a different one. And technically that is log base e. The annoying thing is that there are a lot of textbooks which use an unadorned log for that. And if you use Wolfram Alpha, it will not know necessarily whether you mean common log or log base e. It kind of, the AI goes different ways, different days on that. Yep.
Is there a way to input the base of the log in our calculators?
Yes. Yeah, there should be. So, well, it depends what calculator you got.
I just have the one you told me to buy.
Oh, well, that's good. Let's see here. It'll take me a second. So the common log on this is the button that's log. It's like, for me, it's under x inverse.
Right.
It's like the 1 over from the top right corner, 1 down. So if I do log of 2.6, what I get, oh man, stupid finger. So I get, from the first term, I get something little, about 0.415. Did you get that? Yeah? Cool.
4.1497328.
Yep, very good, very good. And how about the other thing? You shouldn't need a calculator for the other thing, you see? What is the log base 10 of 10 to the 18? remember, log base 10 and 10 to the thing, these are inverse functions. In some sense, they cancel each other out. This is just 18. So log base 10 of x is about 18.415, approximately speaking.
How do we put like a log base 2?
Oh, log base 2?
I guess, how do we put it in a different base? If it's 10,
It is in here. Give me a second here. I know because I thought it wasn't, and then I found it. See if I could find it again. Well, now I start to wonder.
oh wait,
Do you find it?
yeah, I found it.
Oh man,
It's like top right.
you beat me. Oh, yeah, the top right button. Thank you. So yeah, if we do example 6, take our calculators out for a spin here. Like, what's log base 7 of 9? First of all, before we use the calculator, what kind of number should it be? Bigger than 1 or less than 1? What's log base 7 of 7? I heard a 1. Very good. So the graph of log base 7 looks something like this, right? So this is when we input 1, log base 7 is 7. Is 1. So if we're to 9, it's like here-ish, you know? So I expect the number to be, I don't know, 1.1 maybe? What is it actually though? Did you figure it out? 1.129. So I was a little bit off. All right, so something like this, you really have no choice but to use your calculator, all right? But there's a lot of expressions using logarithm or exponential where we can do exact mathematics using properties of the log and the exponential. So we should try to do some examples like that, right? I'm sure I've assigned some of these in your homework. Sadly, I forgot to take a picture of your book before I came here today, so I don't have the problems to scroll through, but I can make some up. I'm pretty sure my problems will be like their problems, give or take. All right, so here's one. Let us calculate, let's see here, the log base 3 of 9 divided by the cube root of 3. So I would use the property of log personally. I would rewrite this as, well, you got log base 3 of 9 minus log base 3 of 3, the cube root of 3, right? Since you're working with log base 3, you want to convert everything to powers of 3 if you can, all right? So 9 is what? We got to have some number sense here. So 9 is 3 squared, right? And then by the definition of the root 3 function, that's 3 to the 1/3. So what do we have? We have 2 from the first one, right? And minus 1/3 from the second one. And then, of course, we don't like to leave our answer like that. So we got what? 6/3 minus 1/3. The answer is 5/3. Now, of course, you could numerically approximate that by just going to your calculator and plugging it in. And you got 5/3 exactly? Good, yeah. See, that calculator's smart. It knows how to do some of these exact things directly. So, let's look at one with natural log. Suppose you're calculating the natural log of e to the 3x times e to the minus x. So I guess at this point I feel guilty. I feel like I should tell you properties of the exponential, right? I have not given those to you yet. Let me give those to you before we go on. See, because there's two ways that we can go on this kind of example. The one is to use the properties of the log to do it. The other is to use the properties of the exponential to do it. You got two choices, all right? So what are the properties of the exponential? So here they are. If we have a to the x times a to the y, what do we get? We get a to the x plus y. If we have a to the x over a to the y, we get a to the x minus y. And finally, if we have a to the x raised to the t power, we get a to the xt. So these are the, laws of exponents that I often find myself needing. Now there are tons of other special ones, right? Like a to the 1 is a to the 0 is 1. These things also matter, of course, but those are your sort of generic. So what can I do here? If I've got e to the 3x times e to the minus x, what does that equal to? See, I have e to the what? 3x minus x, right? I could say e to the 3x plus minus x if you like. What's 3x minus x? E to the 2x, right? And then the answer here is just 2x. Because, this is the definition. If f of x equals e to the x, then f inverse of x is the natural log of x. Natural log is the inverse function of e to the x. So you have equations like this. You have the natural log of e to the, let me use a different letter here. E to the w is equal to w, and you've got e to the natural log of Pac-Man is equal to Pac-Man, provided that Pac-Man is greater than 0. But these are identities that link the exponential and the log. I'll allow it. It's fine. Hey, if my mom calls me in the middle of class, I'm going to pick it up too, So. No. Any questions, guys? All right. Let me do a kind of more advanced example, if you don't mind. Let's try to do some things we haven't done yet. So here's one. This function right here, right? Can we find the inverse function to this function? Now, this may be too hard. I may be jumping ahead a little bit here. What I'm about to do, maybe this is not, you could argue what I'm about to do is inappropriate. It's definitely not inappropriate a week and a half from now, but it might be too much for you right now. So if you don't follow what I'm doing, it's okay. But you want to get to the point where you understand what I'm doing pretty soon. This would not be on the quiz.
This is like a prequel.
A prequel? Yeah, except not horrible. So I'm just so excited about the fourth movie with Ray. Let's see here. I'm just giddy with excitement. 2 log base 2 of x minus 7. as my brother says, they're movies about space wizards for children. Who cares? But Braveheart. Let's see here. So y equals 3. So suppose I want to find the inverse function to this. I need to do what? What was our algorithm? Write y equals f of x. Step number 2, solve for x. How do you solve for x here? You say y minus 3, divide by 2. You've got log base 2 of x minus 7. That is exactly the right first move. That is what you want to do. At this point, we have isolated the logarithm. How do you undo a logarithm? I mean, the answer is kind of right here. See this? This undoes the logarithm, right? A to the whatever undoes log base A. So to undo log base 2, I take the equation and I exponentiate it. To exponentiate an equation is to take both sides, oops, not E, and raise them to that power. So like 2 to the y minus 3 over 2 is equal to 2 to the log base 2 of x minus 7. Just exponentiate both sides. And when I do that, the 2 in the log base 2, they cancel, and you're just left with, on the right-hand side, bless you, x minus 7. All right? And so solve for x. What do we got? X is equal to 7 plus 2 to the y minus 3 over 2.
Oh, okay, I see that.
Oh, okay. And then that's my, there it is. That's the formula for f inverse of y. This is equal to f inverse of y. So there you go. That's the inverse function. So if you have a formula that's built from a logarithm, the inverse function is probably going to be something built from the corresponding exponential function. Yep.
Would it have to be 7 minus 2, y minus 3 over 2, to switch it to the other side if you're also moving x to the other side? Or did you just move 7 over?
I just moved 7 over. Mm-hmm. Question, what's the domain of the inverse function? Which y's can you put into that? The answer is everything. There's no problem. We can put whatever number you want into the the exponential base 2 function. It takes any input. So the answer is everything. What's the range of the original function? Well, it's equal to this. The range of the original function has to be the domain of the inverse function. And conversely, the range of the inverse function, which is not quite obvious, is equal to 7 to infinity, which I erased. But that was, by the way, what we figured out for the domain of the function. So this is another really cool thing about functions and inverse functions, is you can find the domain of one from the range of the other, or you can find the range of one from the domain of the other, vice versa. This is actually really kind of a neat trick, because it's sometimes easier to find a formula for an inverse function than it is to graph a function. And if you can find the formula, then you can like just see where it's not defined and figure out the range of a function from the domain of the inverse. It's kind of a trick. But let me finish class with a couple much easier examples for you guys. All right?
Like a cool down?
Yeah, a cool down. Example 5. Suppose we have